Hello everyone. So this is the first reaction under nucleophilic addition to carbonyl, where the nucleophile, that is which will be added to carbonyl compound, that nucleophile is carbanion. So negative charge present on carbo. Now involving carbanion as nucleophile, there are other reactions also under nucleophilic addition to carbonyl, this topic, but those reactions will be discussed separately. But the common thing among these reactions is the addition of carbanion. Okay, now depending on what type of carbanion we are using, depending on that there will be different types of reaction. Mostly these are name reactions. Okay, so today it will be aldol reaction. Now aldol reaction, it is also called sometimes aldol addition or aldol condensation. So basically here first addition reaction happens and then condensation. So condensation means removal of water molecule, not just always water molecule, that is removal of any small molecule from a large molecule. So that is why the name is condensation. You can also call it dehydration. But first there is addition product. So up to this step it is nucleophilic addition, but there is extra step which is condensation, that is removal of water in this case. So here we have taken two same carbonyl compound. Now it may be different also. That example we will see later. Here both these molecules are same, but we have used two different color. Fine. Now why it is so? Because one molecule will act as nucleophile, that is it will act as donor, it will give electron density, and another molecule which is in purple color, that will be used as electrophile. So it will accept electron density from the nucleophile. Fine. Now you can also call it dimerization, because two same molecules are linked to each other and we are getting this addition product. So if the two molecules, that is the two carbonyl compounds, whether it is aldehyde or ketone, if they are same, we can also call it dimerization. So this is the addition product, and the connection point is with this carbon, this carbonyl carbon of the electrophile, that is the acceptor that is attached, and this CO double bond that is now converted to COH, and one carbanion will be generated at this carbon. Now this reaction, though no reagent is written on this arrow, because it can be acid catalyzed as well as base catalyzed, both are possible, though mostly it is base catalyzed, not acid catalyzed, but acid catalysis, that is also possible. And the second step, it is sometimes it is required to heat the reaction mixture, but it may not be so always. Mostly when it is when it is base, then this dehydration step is not so favorable compared to acid. In that case heating may be required, and this dehydration step compared to the addition step, it is faster and it will drive the whole equilibrium towards the right hand side, because up to addition products, if you consider, it is mainly reversible. The dehydration step is also reversible, but comparatively it is faster. So that is why it will drive the whole equilibrium towards the right hand side. Sometimes we cannot isolate this addition product, but why we cannot isolate? Because the next step is so fast. Fine. But controlling the reaction condition, we can isolate this molecule up to this. That is if we keep the condition mild. Now we will see some aspects of this reaction. Aldehyde or ketone must have alpha hydrogen, because if alpha hydrogen is not present, then carbanion generation at this position, that is not possible. So if it is same aldehyde or ketone, then obviously alpha hydrogen should be present. But suppose two are different, if here it is A plus A, but suppose if it is A plus B, so at least one carbonyl compound should have alpha hydrogen, otherwise how it will that is the carbanion will be generated. Okay, that is not possible. So that is why alpha hydrogen must be present. And why we are talking about alpha hydrogen only? Because with respect to this carbon is alpha, and the hydrogens that are attached to this alpha carbon, they are acidic in nature because of the presence of carbonyl group which is electron withdrawn. So this is the first point. Next is aldol reactions of ketones are less favorable. That is, compared to aldehyde, it is less favorable. So mostly we see that is aldol reaction that is involving aldehydes. So for aldehydes, the reaction is mostly exothermic. So it is faster. Fine. Aldols lose water when heated. So aldols basically the addition product. This is aldol. So it will lose water when heated, and that is why it is condensation. We can also call it dehydration. The formation of stable alpha beta unsaturated carbonyl compound is a driving force for this step. That is this removal of water. What is the driving force? Because this compound is alpha beta unsaturated carbonyl compound. So this portion is alpha beta unsaturated carbonyl compound, and because of resonance this type of moiety is very stable, and that is a driving force. So initial aldol addition product sometimes not isolated, as I have already said, because the next dehydration step is so fast that we cannot get the addition product. We cannot isolate it. The reaction is reversible, both addition and condensation, though condensation is comparatively faster. Okay. Now we will see the mechanism. First, under basic condition, what will be the mechanism that we will see. So here we have taken same carbonyl compound. We will also see different carbonyl that is reaction partner, but right now it is same molecule. So basic condition HO minus, it may be NaOH or KOH, it will capture this alpha hydrogen. This is alpha carbon, so the hydrogen is alpha hydrogen, and there will be CC double bond, negative charge over oxygen. So this is enol, and water is generated. Now this enol, this is actually donor, and another molecule which is in purple color that will accept electron density. So it is accepted. Okay. Now it will attack here. There will be O negative. So there is O negative charge. Finally, it will take proton from water, and HO minus will be formed. Now this type of protonation, why it is possible? Because this is alkoxide, and alkoxide is comparatively stronger base. If you compare the basicity of alkoxide and HO minus, alkoxide is stronger. So that is why it can capture proton from H2O minus, and HO minus can be generated. Normally HO minus is not a very good leaving group, but still it is produced because of this reason, because aldehyde is stronger base compared to HO minus. So it can capture H from H2. Next, dehydration step, because up to this point it is addition product, right? But after this step, this will be the next step is dehydration. So this, from this addition product, that is beta hydroxy aldehyde or ketone, depending on what type of molecule we have taken. Why it is beta hydroxy? Because this is alpha, this is beta, at beta position there is hydroxy group, so that is why it is beta hydroxy carbonyl compound. Dehydration step under basic condition. Normally dehydration it is done under acidic condition, but in this case base catalyzed dehydration, that is also possible. Now see how it is. So HO minus, it will capture another alpha hydrogen. Now remember here, this second alpha hydrogen, it must be present, because if this hydrogen is not present, then water elimination is not possible, right? So under that condition we will get product up to this, because further elimination of water is not possible. So here first enolization will take place. You can also write here the negative charge over carbon, and directly you can push this HO minus, but it is more logical that first we write the enol, and then this negative charge will be pushed, this double bond will be shifted, and OH will be removed. Okay, so in this way, that is a proper mechanism, more logical. And finally we are getting alpha beta unsaturated carbonyl compound. This is alpha, this is beta. So this is a base catalysis. Next we will see acid catalysis. Under acidic condition, First, there will be protonation of this oxygen. So when it is protonated, there is positive charge. Finally, in presence of H2O, this hydrogen will be removed. And there is enol. So this is enol. And this hydrogen will be taken by this water. It will be converted to H2O plus. Now this enol is our donor. And this is acceptor. Now see, acceptor is already protonated. I have already written it as protonated because under acidic condition it will remain protonated, and this carbon is now more electropositive because of the presence of positive charge over oxygen. Now this enol, it will act as donor. Oxygen is neutral now. This oxygen is neutral and this oxygen is positively charged. Finally, H2O, it will capture this extra proton. Oxygen will be again neutral. So this is our addition product, that is beta hydroxy carbonyl compound. Now this hydrogen is the second alpha hydrogen. So dehydration will take place. So this hydrogen, first there will be protonation of this OH, because now we do not have HO minus, we have H plus. So this will be protonated and this hydrogen will be removed. So this is removal of water as well as minus H plus. Finally, we are getting the condensation product, that is alpha beta unsaturated carbonyl compound. Now we will see that two different aldehyde when taken, not just aldehyde, it may be ketone also, or one is ketone, another one is aldehyde, then the reaction will be called as crossed aldol or mixed aldol. Fine. So here we have taken acetaldehyde. So here we have only one methyl group and here we have ethyl group, CH3CH2. So two different aldehyde. Now in the left hand side, the product mixture that you are seeing, that is actually from the same molecule. So the blue product, that is actually from two molecules of this A. Suppose this is A, this is B. So 2A dimerized to this beta hydroxy carbonyl compound, and 2B, that is dimerized, that is same self condensation, not condensation, sorry, this is beta hydroxy carbonyl compound. I have not written the condensation step, that can also be done, but here we have to see that what type of addition product we are getting first. So this is the self reaction, that is dimerization. But if A is acting as acceptor, A is acceptor and B is donor, then we will get the first compound, this one. And here you can see this is B, this is actually acceptor, and the blue part, that is donor. So now A is donor. Fine. So depending on that, that is different types of sometimes A is acting as nucleophile, sometimes B is acting as nucleophile. So depending on these, all these possibilities, here we are getting 4 different types of product, right? But if that is how we can control this reaction, that we will also discuss. But if we are getting this type of product mixture, then obviously aldol reaction, it will not be of any synthetic value, because we are getting mixture of product and it is difficult to separate the compounds. Fine. And yield will also be not good. So how to control this crossed or mixed reaction? Yes, it is possible. One thing is that if one of the carbonyl molecule, not aldehyde, if one of the if one of the carbonyl compound is more reactive compared to the other. Now it may be that you have taken one aldehyde and one ketone. So obviously aldehyde is more reactive from electronic point of view as well as steric point of view. So aldehyde, that will be acting as acceptor. That is one possibility. Another thing is that if alpha hydrogen is not present in one of the carbonyl compound, then also some product, that is here we are getting all these different types of products, then we will get one major product. Okay, so we will see one example here. Crossed aldol reaction, how it can be synthetically useful if it gives good yield of a single product. So here we have taken the acceptor which is aldehyde, but here at alpha position there is no hydrogen. That is why it is non-enolizable aldehyde, and it can act only as acceptor. It cannot act as donor because carbanion we cannot generate. But here we have 3 alpha hydrogen. So it is enolizable, and that is why it can act as donor. Now when it is acting as donor and this is acting as acceptor, the major product will be this one. Fine. Now one question may arise in your mind, that there is self reaction possible between two acetaldehyde molecule, two CH3CHO molecule, they can react with each other. Now to avoid that, there is one process that we can do. And what is that? What we will do, we will add the enolizable carbonyl compound slowly to the mixture of non-enolizable carbonyl compound and alkali. If it is A and it is B, then A will be first taken with alkali. It may be acid also. I am writing here alkali. And B will be added slowly. Now why it is so? Because only enol can be generated only from B. Now if B is present in small amount, it will be only in enol condition, that is carbanion, and this carbanion that will react with A. Because carbanion generation in A, that is not possible, and self reaction between two A molecule, that is also not possible. That is possible only between two B molecule. So that is why we will add it slowly, because the small amount of B in enol form, it can completely react with A, and then another drop of B will be added. It will also again react with A, because A is present in excess, B is added slowly. So in this way we can avoid the self-aldol reaction of B. Self-aldol reaction, it is possible only for B, not for A. Some amount of product will be formed, but that will be minor. So these are the process by which we can make crossed aldol synthetically useful. Here another thing I want to mention, that is, if we have taken aryl aldehyde as one of the carbonyl compound, then the reaction is known as Claisen-Smith reaction. So on the left hand side we have taken ketone. So this is actually non-enolizable because there is no alpha hydrogen, aryl halide, and here we have taken aldehyde. So both two possibilities I have written here, but the main thing is, if one of the reaction partner is ARCHO, that is aromatic aldehyde, then the reaction will be called as Claisen-Smith reaction also. Okay. We will see some examples of effective crossed aldol condensation. Normally crossed aldol condensation, it is not synthetically useful, but in some cases it may be synthetically useful. How it is possible? Here we have taken acetone, this is ketone, and benzaldehyde. Now this is non-enolizable, so carbanion generation is possible only in acetone. Now this carbanion, when it will react with this carbonyl compound, here also we can add these acetones slowly to benzaldehyde to avoid the self condensation between two acetone. So first there will be production of this alpha beta unsaturated carbonyl compound. Now in the left hand side another methyl group is present, so in the left hand side also another reaction, another aldol reaction, that is aldol condensation, is possible. So that is why here this is the end product. Fine. If we have taken benzaldehyde in excess, because this will be 1:2 reaction, that is we have to take PHCHO more compared to acetone, because from the two side of acetone there is condensation reaction going on. Okay, this is the first example. Next example is interesting because here we have taken CH3CH2CHO. Okay, this is enolizable. This is enolizable. that is carbanion generation is possible, but this is not. And formaldehyde we have taken 2 molecules. Why? It is taken in excess. There is a specific reason for that. And also see here the reaction condition is mild and it is not 10% anyway. It is dilute. Compared to 10%, it is dilute and milder condition, because for this dehydration step, we have to heat it, but 25 degrees centigrade is room temperature. So when the condition is mild, then we are getting only the beta hydroxy carbonyl compound, and as there are 2 alpha hydrogen, so 2 times aldol addition possible. Here only aldol addition is going on, here no dehydration, because after the first addition, in this position there will be 1 hydrogen. Okay, so this hydrogen can be removed along with this OH as water, but that reaction will not take place, because this another hydrogen, that is the second hydrogen, that will also react with another formaldehyde molecule, because it is present in excess and the condition is mild. That is why dehydration will not take place and we will get this type of molecule. 2 alpha hydrogen, both are now substituted by CH2OH. And the last example, what is unique point here is right hand side 2 alpha hydrogen, left hand side 1 alpha hydrogen. We are using basic condition. Now among these 2 different types of alpha hydrogen, these 2 hydrogens are more acidic. Both are acidic in nature, but it is more acidic because here we have donating group which will decrease the acidity of this H. Now as it is more acidic, so in presence of basic condition, carbanion will be generated only at the right hand side carbon, and that is why we will get this type of product where the substitution is on, where the addition is on the left hand side. Actually aldol reaction you can also call it substitution of alpha hydrogen, because if you consider from the donor point of view, this is our donor, right? So if you consider from the donor point of view, then it is alpha substitution of, that is alpha hydrogen, that is substituted by this type of group. Okay, so you can also call it from the donor point of view that it is substitution, but as we are discussing it under nucleophilic addition reaction to carbonyl, so that is why we will consider it in that way. Now from this, if you consider the purple molecule which is acceptor, so here it will accept electron density from this carbonyl which will be generated on this carbon, and this PHCHO, that is the attack will be here, and here addition will take place. So from this purple molecule, that is the acceptor molecule, it is addition reaction. So we can call it alpha substitution of carbonyl compound, or we can also call it addition, but we are focusing on addition because we are discussing the reaction under nucleophilic addition to carbonyl compounds. Fine. So come to the point where we have left here. Right hand side reaction is going on, but you can think that why not reaction at the left hand side? One reason is it is less acidic, but even if some amount of product is formed, suppose some amount of product is formed, this is OH, but see here second alpha hydrogen at this position, there is no second alpha hydrogen. So even if this addition product is formed, this is addition product beta hydroxycarbonyl compound, even if this addition product is formed, here dehydration is not possible and we cannot get alpha beta unsaturated carbonyl compound. So that is why, as it is reversible in nature, even if the addition product is formed, it will come back again to this side, because dehydration in the left hand side alpha position, that is possible, and as dehydration is faster compared to addition step, it will drive the reaction towards this side, that is addition will be only from this alpha side, not the left hand side. Okay, this will be formed, and as the reaction is reversible, it will again be converted to the initial starting material, because dehydration after dehydration, this compound we will get this dehydration step that will drive the reaction towards right hand side. Okay, so this is not the end of aldol reaction, because this is very important reaction. We will see some applications and also some examples in the next video. Okay, so if you find the video helpful, please like, share and subscribe. All the important links of playlist you will find in the description box. I'll meet you in the next video. Thank you for your time.